Okay, here I am again. All right. So everybody looks like everybody all got their tests in. Maybe I gotta double check everything, and I will be getting to the grades by next couple days. Just trying to get everything organized. I have 4 courses I'm teaching, and six classes. So it's a little overwhelming getting this all going, but I know you guys are just the same. So next thing we're gonna do is start talking about how chemistry takes place. So up to now, what we've been doing is been looking at chemistry from our point of view, and that means actually hands-on, where we know the chemical names, chemical formulas, and we can actually go look for them in the cabinets and bring out calcium carbonate, etc. And then we can mix things together, those chemical reactions, and we can write those as chemical equations. And we talked about different kinds of chemical reactions: single replacement, double replacement, combustion, and acid base. And then we finished off last week with stoichiometry, and that's how we can actually measure out and do experiments to get appropriate amounts of stuff that we want in chemistry, which is what chemistry is about. It's about producing stuff as well as okay. Up to this point, we talked about is that the major driver of most chemical reactions is oxidation reduction. So in single replacement and combustion, where one substance gains a negative charge, becomes reduced, and another substance loses negative charge and becomes oxidized. These two things work in tandem, and what that means is if something gives up a negative charge, another substance will pick up the negative charge. And this isn't just some random event. What we want to know is that if it's not random, then what is the specificity behind it? Why are some atoms better at taking electrons, and why are some better at losing electrons? And that's what we're going to start looking at now. So one of the key things that's going to help us focus on this is the relationship between structure and function. The structure of a thing will very often define what it does. For instance, a Corvette is built for speed, and you can just look at it and know that it will drive fast. Okay, a semi, on the other hand, both semis at least, are built to carry tons of stuff, and you pretty much, if you were to look at the two, you could probably guess which one is going to be able to do what. And that's because its structure determines what it's going to do. So the structure of a thing often is formed in a very specific way so that something can do its job, or a function. So structure, function. And that's what we're going to be getting into. So what we're going to do is that maybe help explain oxidation reduction. What we're going to do is go to the atomic level and see if we can figure out why, what is it about the atomic structure that allows an atom to be oxidized or reduced. So what we're going to go down is the very small, very, very tiny bits, and we're going to look at the atomic structure to find out what makes it good at giving or taking electrons. And this should be wrapped up in its structure, because structure determines what it's going to do. So what we're going to study first is the structure of the atoms, and really the electronic structure. And what I mean that is how the electrons are structured around the atom. And then after that, we're going to talk about how that relates to oxidation and reduction. So I got 4 PowerPoints here that we're going to put up that's going to talk about the structure of the structure of the electrons around atoms. And then the next series of PowerPoints, which I'll get to by the end of the week, which will give show how the structure relates to the function. Okay, all right. Now, for a really long time, we really didn't know that there were atoms. We thought there's all kinds of different ideas of the world, that had ways of explaining the world throughout time. And it's only been over the last 120 years or so that we've really come to understand what the world is made of and the concept of an atom. And it started out pretty much, what I'm going to start out with is something called a solar system model. And I would just give you a little bit of history to show you how we got to where we are now. You won't have to know this history. I'll tell you what you will have to know from all these slides here. But just hang in there with me and I'll go through it. So there was this guy about 1910. His name was Ernest Rutherford. He was actually a fellow from New Zealand that worked at Cambridge University in England. And what he did is he discovered that there were protons. And he suggested a model of atoms based on the proton. Now, actually, electrons had been discovered a few years earlier by his boss, J.J. Thomson. Up until Rutherford's discovery, atoms were thought to be solid, so they just thought they were like balls, solid balls. But with Rutherford's experiment, what he realized that an atom is mostly empty space, and that most of the mass was actually inside the nucleus. And we'll see how that relates to the solar system in a minute. But you kind of can think about it. It's just like a solar system. We have the sun, which actually contains most of the mass of the universe, of the solar system. And then there's wide areas of spaces between the planets. So the protons contribute to most of the space because they're in the nucleus. And then what he said, the electrons fly around the nucleus at quite a distance. And then it was kind of suggested that the nucleus, what we have is a solar system model, where the nucleus was like the sun. The nucleus had the protons. Neutrons had not been discovered yet. And electrons were like planets going around. So let's just study this model and see how we can relate it. It's not really the best model, but it will help us get to where we need to go. Okay, so let's look at the solar system. Planets go around the sun. And so what I want to ask is this. Why don't the planets fly off into space? Okay, another way you can say that, why do they circle at a particular distance around the sun? So we all probably see you have the sun, and then you have the electrons going around the sun. And why does that take place? Why don't the planets? Why don't the planets fly off into space? Why do they keep going around a circle? And why do they keep that specific distance? Okay, why is the Earth this far from the sun, and why is another planet this far from the sun? And there's different reasons, but we're going to just kind of give one reason. Okay, now the main reason why the Earth and Sun are where they are is because they are attracted to each other. And this attraction is called gravity. Okay, and it's the same gravity that affects things here on Earth. For instance, when something falls to Earth, like a pencil, if you dropped a pencil, it would fall to the Earth. And the reason why it falls to the Earth is because the pencil and the Earth are attracted to each other. And so the pencil is attracted to the Earth. So overall, what we say is things with mass, anything with mass, will be attracted to each other. So any piece of matter are all attracted to each other. We don't notice it. Like if I had, two balls and I have them both in my hand, you won't feel them pulling on each other. And that's because the attraction between them is very, very weak. But if they were very, 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 very large, like two planets, you would see them pulling towards each other. Okay, so the attraction is dependent on how massive they are. Okay, so we have the Earth we're this far from the sun, and like I said, it's being attracted to the sun by gravity, just like pencil dropping the Earth. The question is, if you drop a pen, if you have a pencil, it'll fall to the earth. Well, or fall to the ground. That's because the pencil is attracted to the earth, or the mass of the earth. Well, the earth and sun both are giant pieces of mass, and they're attracted to each other. Why don't they come slamming into each other? Because they're both attracted. Okay, so the way I'm going to kind of think about this is, think about a ball that's on a compressed spring that you're going to swing around. So you can take it and hold it in your hand, and then what you're going to do is just swing it. And essentially what's the thing that's making the ball where it is close to your hand is the spring. Okay, so the attraction between your hand and the ball is the spring. All right, now if you take the ball and you start moving it through the air, what you'll notice is that the spring will start to extend. Okay, and it'll start to move further away. So if you swing it, what you'll see is the spring will start to extend. And as it extends, the ball will get further away. If you swing it faster, the spring will extend even further. Okay, but it still will stay attached. So the faster the ball moves, the longer the spring extends. Now if you slow down the swinging, the spring will collapse some and the ball will move closer to your hand. So it seems the speed of the movement counteracts the effect of the spring's pull. And you can see that diagram here. So let's say this is our starting point, and you have a spring. Here's your hand up here, and here's the ball. And what you do is you start to swing it, and as you swing it, the ball extends further out. Okay, the spring has a harder time holding on the ball because it's moving faster. And if you move the ball in faster, the spring will extend even more, but it'll still attach. So what is happening is the spring is exerting an attractive force. Okay, so the spring is pulling the ball towards my hand, but on the other hand, the speed of the ball is pulling the ball away from my hand. And so they're balanced. They're not balanced each other out, but they counteract each other. So, and that's what we're going to see with the Earth and the Sun, and eventually electrons and protons. For the Earth and the Sun, you don't have a spring; you have gravity. And here's the Earth, and here's the Sun. Okay, and as the faster the Earth, let's say if the Earth started to speed up, it would move further and further away, but it'd still be attracted to the Sun, and it would keep going around in circles. All right. Okay, so what we get is a picture like this. All right, where the Earth is being attracted to the Sun, but it's not being pulled, not being collapsing in the Sun, because the speed of the Earth is keeping it away. And why it's keeping this distance has to do with how fast it's going. Now, if the Earth were to speed up, it would move further away. Okay. All right. Now, the next thing we'll consider. So you have what you have is you have the Earth going around the Sun, and the reason why it keeps that is there's two things going on. The Sun is pulling the Earth with gravity, and Earth is pulling away from the Sun because of its speed. Okay, and so it keeps in a orbit based on how fast it's moving. All right, another thing that we want to take a look at is the natural tendency of attractions. When two things are attracted to each other, they want to be close together. Now, I use the word want. Now, we'll go through the examples, but for instance, when you have a ball and you're holding if you're holding a pencil, and you let it go, it sort of wants to be close to the Earth. Okay, moving objects away from each other doesn't seem natural. So when you pick up the pencil and move it, it's unnatural for it. It'd rather kind of be back on the ground. Now you feel, in this case, what you do is you would actually feel the earth kind of pulling on the pencil. You can feel that when you pick the pencil up. You can feel that it requires some sort of force to pull it away from the earth. Okay, and it's almost like the earth and the object are calling to each other. It's saying, let me go, and they kind of they're strained. There's a stress on the object. It doesn't want to be away from, in this case, a pencil doesn't want to be away from the earth. It has some internal stress, just like we have internal stress. Like if somebody says, they take your baby away from you, okay, you're gonna feel upset about it, okay, and then if the baby comes back to you, you feel relieved, and that's sort of what's happening here. This internal stress is called potential energy. Okay, as attracted things are moved away from which they gain stress or potential energy. Naturally attracted objects want to be close to each other so they can relieve their potential energy or their stress. When attracted things are allowed to collapse back on each other, they release the stress as real energy, and that causes things to happen. For instance, if you raise a book 3 feet off the table and then let it go, it will hit the table and shake it at the table a little bit. Now, if you take the same book and you raise it 10 feet off the table and drop it, it'll make a louder sound and shake things a whole lot more. What it did is it was really stressed being 10 feet away from the table, and it released that stress as energy, and now that the book is less stressed. And so the higher book originally had more stress than the lower book had less stress, which we say is potential energy. And we use the word happier, but really what it means is more stable. So I'll use the word stable and happier in the same kind of terms, and stress and potential energy is kind of the same words. Okay, one of Rutherford's students, a fellow from Denmark named Niels Bohr, what he did was try to figure out specifically the structure of the atom. So he wanted to expand on Rutherford's idea, and he's the one that really developed the solar system model. And basically what he said is electrons move around the proton in orbit, and he wanted to be very specific about it. He said that the electrons and protons were attracted to each other not because of gravity, but because of opposite electrical charge. So a proton has positive charge, and electron has negative charge, and they're attracted to each other. They want to be close together. Okay, so just like with the planets from the sun, the distance the electrons are from the protons is determined how fast they are moving. Okay, the faster they move, the farther away from the protons be. The faster ones could be, just like I said, are further away, and the slower electrons would be closer to the protons. So that's a good place to start. So you might have electrons that are close to the protons, and what they're doing is they're not moving as fast. And then you have guys moving that are further apart from the protons because they're moving faster. And here's a picture of kind of like the solar system of an atom. You have the protons and electrons are attracted to each other, just like gravity. It's not the same thing as gravity, but it's still a forced attraction. And the electrons are moving at a certain speed. Now, if you increase the speed, this orbit will be bigger, and if you decrease it, it'll be smaller. Okay. Now, one of the key things about Bohr's idea is that, all right, based on experimental evidence, what he realized is that electrons just can't be at just any distance, any distances from the protons. They have to be very specific distances from the protons. These distances are very specific and exact. You know, there might be one electron that's 1 mile away, another one that's 2 miles away, but you can't have an electron that's 1.5 miles away. It just has to be a mile or 2 miles. Okay, I'm just saying the mile or 2 miles. It's a lot smaller than that, but you can't have it's in very discrete distances, and they can't be found any other. And this was a major breakthrough in understanding the structure of an atom, and he called it the quantum model. Okay, so what we have is you can kind of imagine it like this. So you have protons, and then you can have an electron in this orbit, this orbit, this orbit, this orbit, and so forth. It could be actually go on for infinity. But the electron can't be found between these orbits. They're either in these guys or not. Okay, so they are stuck here, or they're stuck here, stuck here. Okay. So the other thing is that we're not going to call them orbits anymore, because we're not really sure if they spin around the atom. We actually have a different way of describing it, but we do know that the further electron is away from the proton, it has more stress in it, just like the 10-foot book had more stress in it than a 3-foot book. So what we're going to do is we're going to call these levels energy levels. So instead of call orbit 1, orbit 2, we're going to call energy level 1, energy level 2, energy level 3, and energy level 4. And we're actually going to, we'll get to this in a little bit, we're going to not even describe this thing as like the solar system in a little bit, but it's a good place to start. Okay, now suppose you take an electron and drop it into an atom with these 4 pathways. There could be as many. Where would it like to go? Is it going to pick energy level 1, energy level 2, energy level 3, or energy 4? Or does it just pick any of them? Okay. Yes, it's very specific which one it's going to pick. Remember that electrons want to be close to protons because negatives want to be close to positives. So if you drop an electron into an atom, it will naturally want to move to energy level 1 because energy level 1 is the closest to the proton, and it gives that electron the lowest stress potential energy. Electrons will always favor being closer to protons unless there's something that stops them from getting closer. Okay. All right. So let's take a closer look at the model of the atom. So we have these energy levels, and what we want to know is there something specific about the number of electrons can go in each orbital, or what other things do we need to know about these orbitals, energy levels? All right, so let's consider the size of the circle each energy cuts out. So if you take energy level 1 and I took it out, and energy level 2 and cut it out, all right, and put them next to each other, you'll see energy level 1 over here and there's energy level 2. And this guy has a radius of 1. We'll say that's because that's energy level 1, radius 1. So energy level 2 has a radius of 2. Okay, so what we're going to do now is compare the size of the 2 circles. Because what we're going to say is smaller circles are going to be able to hold less things than bigger circles. So what we can do is actually see how many electrons each circle can hold, energy level hold, by looking at looking at the size of the circle. So the size of a circle, the area, is defined by pi r squared. So let's determine the size of each one of the energy level circles. Okay, so energy level 1 has a radius 1, 2, energy level 3, energy level 4. And the area of each one of them, so energy level 1 is an area of 1 pi, energy level 2, 4 pi, energy level 3, 9 pi, and then 16 pi. So 1 squared pi, 2 pi, 2 squared pi, 3 pi squared, 4 pi squared. Okay, and what this says is basically that energy level 2 has 4 times as much areas to put electrons than energy level 1. So if you put 1 electron energy level 1, you could put 4 in energy level 2. Energy level 3 is 9 times bigger than energy level 1. So if 1 went into energy level 1, 9 could go into energy level 3. All right, energy level 1 can have the least amount of electrons, which you might think would just be 1, because that's the smallest number. But it is known that every electron there is basically it has a twin that can live with it. The difference between the twins is one twin, we say, spins up, and the other twin will spin down. So on energy level 1, there can be a maximum of 2 electrons, one up and one spinning down. In energy level 2, since it can hold 4 times as many electrons, it can hold 8 electrons, 4 with up spins and 4 with down. And then we get and so forth. So here's a little table showing that. So energy level 1 has an area of 1 pi, and it can hold 2 things. Energy level 2 is 4 times as big, so it can hold 2 times 4. Energy level 3 can hold 2, same as number 1, but 9 times as much. And energy level 4 can hold 2, the same amount of 1, but 16 times as much energy level 1, or 32 electrons. All right, so that's good. That's the first place to start is the so you have energy levels, and each energy level can hold a different amount of electrons. Energy level can hold 1 can hold 2, energy level 2 can hold 8, and energy level 3 can hold 18. And there's math formulas behind it, and this is actually the only kind of math we'll be doing in this class pretty much in this particular section. And you'll see the formulas when we get. All right, next thing we're going to do is it turns out the energy levels aren't always circles or round. They can change their shapes based on different things. The simplest shape that an electron can exist in is a circle, or since we're dealing with 3 dimensions, it's called a sphere. Okay, and actually this shape here, the shape of the energy level, okay, is called an orbital, s orbital. So the simplest type of place that an electron can live in is an s orbital. Notice I use the word orbital. Don't confuse it with the word orbit. And you'll see how this all fits into place in a minute here. Okay, energy level 2 is bigger. It can hold 8 electrons. Okay, and so since it's bigger, it can be more complex, and it has actually going to have 2 kinds of shapes. It can have S, it can have a sphere shape, and it can have this thing that kind of looks like, we say, a dumbbell, and we call it a p orbital. And the p orbitals actually come in sets in 3. Okay, so the set is called a subshell, and we'll see how this all comes together in a minute. But whenever you have a p orbital, it'll always be with 2 others. So energy level 2 will have an s orbital, a sphere, and 3 p's. Okay, 1, 2, 3, 4. Okay. Now this is going to be significant in a bit, because in each orbital you can put 2 electrons. So you can put 2 here, 2 here, 2 in the p, 2 and 2. So I get 2, 4, 6, 8. How many electrons that we could say go in a second energy level? 8. And this is why. You put 2 in an S and 2 in each piece for 8. Again, you'll see the big picture in a minute. Energy level 3 is even bigger, and it can have more complex. So it has an S. It has the 3 P's, so it has a P subshell with 3 orbitals. And then it also has a D subshell, which has 5 d orbitals. Now you won't have to know about these, draw these shapes or anything. Just know that they are, if a D subshell has 5 orbitals, a P subshell has 3 orbitals, and an S subshell has 1. Now if you count them up, you got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? All right, and you can put 2 electrons in each one of these. 2 times 9 is 18. And how many electrons did we just say could go in energy level 3? 18. Oh, we could go up to energy level 4, and it has the S, the P, the D's, and it also has this group called the F group, which are 7. So if you count those up, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, plus 7 more is 16. And you can put 2 in each of the 16 for 32. And it's exactly what we just said. You could put 32 electrons in energy level 4. All right, so let's piece it together. So energy level 1 has an S subshell, which inside the S subshell is S orbital. Energy level only has one type of subshell, has an S, 1 orbital, and you can put a total of 2 electrons in it. Energy level 2 has 2 types of subshells, S and a P, 2 type, S and P. Has 4 orbitals, 1 S and 3 P's. And you can put 2 electrons in each one of them, so 4 times 2 is 8. Okay, energy level has 3 types of subshells, 3, S, P, and D. And here they are, S, 3 P's, and 5 D's. You add them up, there's 9. And each one of them you can put 2. Energy level 4 has S, P, D, and F. So it has 4 subshells, S, P, D's, and F's. In the S there's 1, P there's 3, D there's 5, F's there's 7. Add those all up, you have 16, and each one you put 32. Okay, and if we go back to our circle diagram, we said the size, here's the size, and we said you could put 2 electrons in the first energy level. Well, that's what we just come up with this, explaining it with orbitals as well. Energy level, we said energy level 2 could have 8 because of its size. Well, yes, it can have 8 because it has S and 3 P's, and each one of these orbitals can have 2 electrons. So every orbital can have 2 electrons at max. It can have 0, 1, or 2 electrons. So orbital will always have no more than 2 electrons. So energy level 1 has an S orbital, and it can have 2 electrons at the most. Energy level 2 has 4 orbitals, an S and 3 P's. So there can be 2 electrons put in each one. So that's going to be 2, 4 times, or 8. Okay, so let's put this together in terms of the big picture of how all these guys fit together. So you have an atom. So this is what we call a nesting diagram, and then you kind of think of the Russian dolls You have those wooden Russian dolls. You open up, and there's mama. You open it up, and there's daughter, and you open up daughter, and there's next daughter, and then they open up, and then finally get little baby. It's the same kind of thing here. So an atom, this outer part is the atom, and within an atom is the energy levels. Energy level 1, energy 2, energy level 3, energy level 4, and so forth. In the energy levels, there's subshells. Energy level 1 has S subshell, energy level 2 has a S and P subshell, energy level 3 has a SP and D, and so forth. And then inside the subshells, there's orbitals. An S subshell has 1 orbital, a P orbital has 3, a P subshell has 3 orbitals, a D subshell has 5, and so forth. And each orbital can have up to 2 electrons, and electrons can have either up or down spin. Okay, so this is sort of the math relationship of how these things work together. So the number of subshells that an energy level can have is equal to its energy level. So energy level 1 has 1 subshell, an S. Energy level 2 has 2 subshells, S and a P. Energy level 3 has 3 subshells, S, P, and D. Energy level 4 has 4 subshells, S, P, D, and F. Okay, now the number of orbitals that an energy level has is equal to the square of the energy level. So energy level 1 has, how many orbitals does it have? Just square it, 1. Energy level 2, how many orbitals it has 4 orbitals. It has 1 S and 3 P's. Energy level 3 has 3 squared. That's 1 S, 3 P's, and 5 D's. Okay? Right, the maximum number of electrons in an energy level is 2 times that number. So energy level 1 can have 2 times the amount of orbitals. So it has 2 times 1. Energy level 2, since you can put 2 electrons in each orbital, it can have a total of 8 electrons. Energy level 3, since it can have 9 orbitals, can have 18 electrons. And we'll do a practice here. How many electrons can go in energy level and can go into an F orbital? Okay. All right. Now, the key word here is orbital. Whenever you hear orbital, the orbital can only take 2 electrons. Okay, that's it. How many electrons go into a 4D subshell? Okay, well, you don't have to worry about the 4. Just look at the D subshell. The D subshell has 5 orbitals, and it doesn't matter if it's a 5D, 3D, 6D, or whatever. All D subshells will have 5 orbitals, and each orbital you can put 2, so there'll be 10 electrons you can put in a D subshell. Okay. If I would ask how many electrons would go into a 4P subshell, you would say 6. Okay, because there's a P subshell has 3 orbitals, and each orbital can hold 2, so you do 2 3 times. So the energy level doesn't matter here. And up here, neither one of these matters. It's this word here, orbital, makes a difference. How many electrons go into energy level 3? Okay, so you can go back and look at the formula, but it's going to be 3 squared, 9 times 2, so 18. So there could be 9 orbitals, 3 squared, and then you could put 2 in each one. And how many subshells go in energy level 2? The number of subshells is equal to the energy level, so you can only have 2 subshells in energy level 2. And that is at S and P. Energy level, let's do another example. Energy level 10, how many subshells can it have? 10. Okay, so that finished this section off, and we'll use it, apply it in the next slideshow.